rocket is shot upward from ground level with an initial velocity of 256 feet per second. Click the Animate button to launch the rocket. While the rocket is in flight, click on the Get Data Point button several times. This will record the height of the rocket at specific points in time. Now take a few minutes to answer some questions. Question 1. The height of the rocket, h of t, is a function of the time t in seconds after launch. The height can be modeled by h of t equals negative 16t squared plus 256t. Determine the values of h of 2, h of 8, and h of 10. To find h of 2, substitute 2 for t in the function. I have h of 2 equals negative 16 times 2 squared plus 256 times 2, which equals 448. This means that 2 seconds after launch, the rocket will be at a height of 448 feet. To find h of 8, substitute 8 for t. I have h of 8 equals negative 16 times 8 squared plus 256 times 8. This equals 1024. This means that 8 seconds after launch, the rocket will be at a height of 1,024 feet. To find h of 10, substitute 10 for t. I have h of 10 equals negative 16 times 10 squared plus 256 times 10, which equals 960. This means that 10 seconds after launch, the rocket will be at a height of 960 feet. Question 2. Interpret the value h of 12 equals 768. In this expression, 12 is the value of t, and 768 is the value of h of t. Therefore, 12 seconds after launch, the rocket will be at a height of 768 feet. Question 3. Determine the time at which the rocket will hit the ground. When the rocket is at ground level, the value of the height is 0 feet. So I can set h of t equals 0 and solve the resulting equation for t. I have negative 16t squared plus 256t equals 0. This is a quadratic equation, so I'll set one side of the equation equal to 0 and factor the other side. Factoring out negative 16t, I have negative 16t times the quantity, t minus 16, equals 0. Setting each factor to 0, I have negative 16t equals 0, and the quantity t minus 16 equals 0. We have two solutions, t equals 0 and t equals 16. The solution t equals 0 corresponds to the time of launch, whereas t equals 16 is the time that the rocket returns to ground level. So the rocket will hit the ground 16 seconds after launch. Question 4. Determine the times at which the rocket is at a height of 880 feet. In this example, we're given information about the height of the rocket, so I'll set h of t equals 880. We have a quadratic equation, so I want to move all terms to one side of the equation so that the other side is 0. I'll add 16t squared to both sides, and I'll subtract 256t. This gives me 16t squared minus 256t plus 880 equals 0. I'll factor the left-hand side by first removing the greatest common factor of 16. This makes the resulting trinomial much easier to factor. I have 16 times the quantity, t squared minus 16t plus 55 equals 0. Factoring further, I get 16 times the quantity t minus 5 times the quantity t minus 11 equals 0. Therefore, the solutions are t equals 5 and t equals 11. So the rocket will be at a height of 880 feet, 5 seconds after launch, which is on the way up, and then again 11 seconds after launch on the way back down. Question 5. Based on the location of the T-intercepts, how many seconds after liftoff will the rocket be at its highest point? Then determine the maximum height. To answer this question, we'll use a little common sense. From the graph, we see that the rocket will reach its highest point at a time halfway between the T-intercepts. This occurs 8 seconds after launch. The height after 8 seconds is given by h of 8, which we found in question 1 to be 1,024 feet. So the rocket reaches its maximum height of 1,024 feet at a time 8 seconds after launch. Now we'll talk more about the graphs of quadratic functions in a later chapter. In particular, we'll talk about the symmetry of the graph, and we'll learn how to find the vertex of a parabola by using analytical methods. So this animation gives us the background for great things to come.